Have you ever wondered how to determine the 3 dB cutoff frequency of a laser or optical modulator? Hi, I'm Marcel, Product Planner for Photonic Test and Measurement Instruments with Keysight Technologies. And today I'm going to show you how you can quickly and accurately measure the frequency response of an optical transmitter. What you will need for this is a network analyzer to stimulate the transmitter and analyze the response from my calibrated photodiode. For the calibrated photodiode, I'm going to use Keysight's N4377A Lightwave Detector. For the network analyzer, I'm going to use Keysight's N4377B PNA. However, the entire test concept is also applicable to all other vector network analyzers from Keysight. For this demo, my device under test will be the 81492A reference transmitter from Keysight. So let's get started. First, you need to decide about the frequency settings for your measurement. That is the start, stop and step frequency as well as the IF bandwidth. The more points you want to measure or the narrower the IF bandwidth, the longer the measurement will take. For this demo, I'll set a start frequency of 100 MHz and a stop frequency of 50 GHz. I will set the frequency step of 100 MHz, thus the total measurement points will be 500. I will set an IF bandwidth of 300 Hz to keep the measurement time short. You also need to choose the RF drive power for your measurement. Here I will use -5 dBm. Now that all basic settings have been made, the network analyzer can be calibrated. This can easily be done with an electronic calibration module. In my case, I have done this already with the same settings as we just entered. This is indicated with a C symbol in the status bar down here. If you don't know how to use an electronic calibration module, follow the link in the description to watch a video on how to calibrate a PNA easily with an electronic calibration module. After the calibration, the device under test can be connected with the PNA and the Lightwave detector. Don't forget to use a torque wrench to tighten all RF connections. In this setup, the device under test is connected to port 1 of the PNA. The Lightwave detector is connected to port 4 of the PNA. The optical output of the reference transmitter is connected to the optical input of the Lightwave detector. Now, let's change the S11 measurement trace to the S41 measurement trace to see the actual electro-optical transmission measurement data. Right-click on the S11 label, click on Measure, select S41 and click OK. The setup is now ready for measuring. For that, a single sweep is performed. Now, the frequency response of our optical path, that is that of the reference transmitter and the Lightwave detector, can already be seen. To obtain the frequency response of the reference transmitter alone, the response of the Lightwave detector needs to be removed from the measurement data. To do that, a touchstone file describing the frequency response of the Lightwave detector can be de-embedded. This file is stored on a USB mass storage inside the Lightwave detector. Let's de-embed it now. For that, let's go to Cal, Fixtures, Fixture Setup. Here, let's right-click after port 4 and select Add Block. This block will be a de-embedding block and we want to use a touchstone file, so we leave the first 2 rows unchanged. Let's select the touchstone file on the Lightwave detector by clicking on the button after file name. Since the reference transmitter operates at 1550 nanometers, we select the corresponding file. Click OK and apply fixtures. You might have noticed that the S41 curve now moved upwards. This means that the response of the Lightwave detector has been de-embedded and the results we now see are really those of the device under test only. There you have it. That's how simple you can measure the frequency response of an optical transmitter with the PNA and the Lightwave detector. Thanks for watching, and visit keysight.com to learn more about Keysight's photonic test and measurement products.